electron displacement changes, especially in organic chemistry. Let us begin with the term inductive effects. The first one, inductive effects. Inductive effects. It is the same as I effects. I effects or inductive effects. What's meant by inductive effects or I effects? Let us take the case of a molecule in which there is a polar covalent bond. You take a molecule like this, CH3, CH2, 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 Cl, a molecule like this. That is chlorobutane. The name will study later. Don't worry. So there is a compound like this. I shall draw the complete structural formula. Complete structure is like this. CH3, sigma covalent bonds between carbon and hydrogen. Then the catenation of hydrogen, carbon. Here also carbon-hydrogen bond CH2. So 1, 2, 3, 4 carbon atoms. And finally we have the chlorine atom. And that is the structural formula of the compound given. The complete structure is given. And that is our chlorobutane. Now you consider the carbon-chlorine covalent bond. You consider this bond, the carbon-chlorine covalent bonds. We know between the carbon and the chlorine atoms, there is a pair of electrons. And the electron pair will be attracted by both the atoms. And the power to attract a shared pair of electrons present in a covalent bond, that's called electronegativity. It's called electronegativity. So electronegativity is a measure of the power of an atom to attract a shared pair of electrons present in a covalent bond. Now you come to these carbon-chlorine bonds. In the carbon-chlorine bond also there is a pair of shared electrons. And both the atoms, that is carbon as well as chlorine, both the atoms will be pulling the electrons, attracting the electrons with their own power. Or in other words, chlorine and the carbon have their own electronegativity values. But you can see that here chlorine is more electronegative. Chlorine is more electronegative than carbon. Chlorine is more electronegative than carbon. So what happens to the electron pair present in the carbon-chlorine bond? Chlorine is more electronegative than carbon, and therefore the electron pair present in the carbon-chlorine bond is shifted towards the chlorine atom. So that what happens to the covalent bond now? Say chlorine gets a partial negative charge and the chlorine gets a partial positive charge. That means the carbon-chlorine covalent bond is a polar bond. It is a polar bond. There is a polar covalent bond in that molecule. Due to the polarity, what happens to the electron pair present in the carbon-carbon chains? Carbon-carbon chain, what happens? Let us mark the carbon atoms say like this. Carbon atom number 1, 2, 3, and 4. Mark the carbon atoms like this. The carbon atom number 1 is having a partial positive charge. Carbon atom number 1 is having a partial positive charge. Due to the partial positive charge on carbon atom number 1, the electron pair presents in the C1C2 bond that is shifted towards carbon atom number 1. Carbon atom numbers, both the carbon atoms have same electronegativity, no doubt. But here, there is an additional phenomenon. That is, due to the polarity of the carbon-chlorine bond, carbon atom number 1 is getting a partial positive charge. Due to the partial positive charge on carbon atom number 1, the electron pair present in the C1C2 bond is shifted towards, carbon atom number 1. And so what happens to carbon atom number 2? It gets a still smaller positive charge, because electron pair is shifted towards carbon atom number 1. Now what happens to the electron pair in the C2C3 bond? What happens? Due to the small positive charge on the second carbon, the electron pair of a C2C3 bond is shifted towards the second carbon, and therefore the third carbon gets a still smaller delta, small delta. Delta and delta, delta, smaller value. Don't think that it is a higher value, smaller value. So delta, delta, delta plus still smaller value is there, positive charge is there. So ultimately what happens here? Due to a polar covalent bond, the electron pair will be shifted along a chain of the atoms. The bonds formed by, see here, there is a chain is formed. A chain is formed by the carbon atoms. Due to the polar covalent bond already present, the electron pairs will be shifted. There is a shifting, a permanent shifting. There is a permanent shifting of electrons. Shifting of electrons along a chain of atoms, along a chain, and that property is called an inductive effect. There is a displacement of electrons. Electrons are displaced along a chain. The sigma electrons, these are the sigma electrons. Why these are called the sigma electrons? These are the electrons present in the sigma bond. It's a sigma bond, coaxial overlap of the atomic orbital, sigma bond. So there is a permanent shifting of electrons along a chain formed by the various atoms. And that permanent shifting of electrons along a chain in one direction. There is only one direction. That is called inductive effect or I effect. So what is inductive effect? Inductive effect is what is inductive effect? Adi, Naurin, Anna, Nia, Donna, all of you are there. Anthony, what is inductive effect? Inductive effect is a permanent shifting, it is permanent, a permanent shifting of electrons along a chain of carbon atoms due to the presence of a polar covalent bond. There is already a polar covalent bond. As a result of the polarity plus minus charges, the electrons present in the chain of the atoms will be shifted along the chain. And this shifting of electrons along a chain of atoms, that is called inductive effect. Okay. You come to chlorine and the carbon again. Here, chlorine is more electronegative and it withdraws electrons. It withdraws electrons. Electrons are pulled towards chlorine atom. And it becomes negatively charged. See here, there is a partial negative charge on the chlorine atom. Because it is having higher electronegativity value. That means chlorine atom is withdrawing electrons. It pulls electrons towards it. Electrons are withdrawn, are pulled by the chlorine atom, and it forms a negatively charged species. That is formation of negative pole. And such atoms or groups which withdraws electrons, pulls electrons towards it, attracts electrons towards it. That is called, such groups are called, electrons are withdrawn. They are called minus I groups. And the inductive effect is called minus I inductive effect or negative inductive effect. Minus I inductive effect or negative inductive effect. That means the electron withdrawing effect. Electrons are withdrawn so that the atom becomes partially negative. So the electron withdrawing inductive effect is called minus I effect, negative inductive effect. So electron withdrawing effect, inductive effect. That's called minus I inductive effect or negative inductive effect. And such groups are minus I groups. Say, for example, halogens, chlorine, bromine, fluorine, iodine, etc. All these are electron withdrawing groups. There may be NO2 group, nitro group. That is nitro group. That is electron withdrawing group, nitro group. There will be cyano group, cyano group. That is electron withdrawing group. So any atom or group that withdraws electrons, that is called an electron withdrawing group, and the electron withdrawal inductive effect is called minus I effect or the negative inductive effect. Okay. There are certain groups which can release electrons, which can donate electrons, which can give away electrons. And such groups, electron releasing groups, they are called plus I groups, and the electron releasing inductive effect is called plus I effect or positive inductive effect. Plus I effect. Plus I positive inductive effect. That means the electron releasing effect. Electron releasing, or electrons are donated, electron donating effect. That's called the plus I effect. Why is it called the plus I or positive? That is because when electrons are released, electrons are given away from the atom or group, it becomes partially positive in nature. When electrons are here electrons are removed. So it becomes partially positive. So the electron releasing or electron donating inductive effect is called plus I effect or positive inductive effect. And such groups or atoms, they are called plus I groups or electron releasing groups or electron donating groups. For example, you take a CH3 group or you take a CH2CH3 group like this. These groups are called alkyl groups. Alkyl, ALKYL, ALKYL. Such groups are called alkyl groups. So alkyl groups are electron releasing groups. They are electron donating groups. Let me repeat this. Say, inductive effect means a permanent effect. It's a permanent effect. A permanent shifting, not a complete removal. There is no complete transfer. If there is complete transfer, positive and negative ions will be formed. Then it is not inductive effect. Inductive effect is only a shifting, a slow shifting, of electrons along a chain of atoms due to the presence of a polar covalent bond. So shifting of covalent electrons present in the covalent bond along a chain of atoms due to a polar covalent bond already present. That's called the inductive effect or I effect. If electrons are withdrawn, attracted or pulled, then it is called minus I effect or negative inductive effect. Electron withdrawal, as we have seen in the case of chlorine, electron withdrawal. So it is a negative inductive effect. For example, chlorine, bromine, fluorine, iodine, nitro group, CN, cyanide group, all these are electron withdrawing groups. And they have minus I effect or a negative inductive effect. But there are cases in which electrons are released, not completely transferred. Remember, there is not completely transferred, shifting only. So electrons are released or electrons are donated. I use the term release or donate. It is not the complete transfer. Remember that. Only a shifting. If there is shifting, the electrons must be released from one atom and electrons must be accepted by another atom. Is it not? So, the electron releasing or electron donating inductive effect. That's called plus I inductive effect or positive inductive effect. And such groups are electron releasing groups or electron donating groups or plus I groups. For example, alkyl groups like CH3 group, that is methyl group. Then CH2CH3 group, that is ethyl group. Ethyl, 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 ethyl group, etc. These groups are generally collectively known as alkyl groups because these are derived from alkanes. Now you come to the end of the inductive effect. I told there is a displacement of electron. Say, how long the displacement persists? No, the electron displacement effect, inductive effect, vanishes after 3 carbon atoms normally. So it is seen only up to, it is effectively seen only up to 2-3 carbon atoms. After that, there is no inductive effect. It vanishes. It vanishes there. Beyond the 3 carbon atoms, there is no shifting of electrons. There is no inductive effect. So it vanishes. The shifting vanishes because as the number of the carbon atoms increases, the length of the chain increases, the positive charge on the carbon atom diminishes. The positive charge on the carbon atom diminishes. And so the shifting vanishes after 3 or 4 carbon atoms. It persists only up to maximum 3 carbon atoms. Beyond that, there is no much inductive effect or shifting of electrons. So that is one thing, one electron displacement change that we have to study. Now you come to the second one, and the second, the electron displacement effect, and that is called the electromeric effect. Electromeric. Second one, electromeric effect. Electromeric effect. That is E effect. Electromeric effect or E effect. Electromeric effect. This is a temporary electron displacement. A temporary electron displacement. So, temporary change. Temporary electron displacement. Due to the requirement of a coming nucleophile or electrophile. Displacement due to the requirement of the approaching nucleophile or electrophile. Nucleophile or electrophile. Say a nucleophile is approaching or an electrophile is approaching, then there will be a temporary displacement of electrons. And the temporary displacement is for the pi electrons. Pi electron displacement. Say pi electron displacement. Say pi electron displacement. You know, in the inductive effect, there is sigma electron displacement. But here there is pi electron displacement. So we can see the electromeric effect in the compounds containing carbon-carbon double bond as well as triple bond, multiple bond. There should be pi electrons. Say, for example, let us take, say, C double bond C. Any compound, any carbon compound containing achot, any carbon compound containing carbon-carbon double bond. Now, say a nucleophile. Nucleophile is Nu negative. Nucleophile is approaching the double bond. It is approaching the double bond. Then the nucleophile is approaching the double bond. What will happen to the electrons, pi electrons? The nucleophile is electron rich. The nucleophile is negatively charged, and pi electrons, they are also negatively charged. So when a nucleophile is approaching the carbon-carbon double bond, the electrons will be displaced to the neighboring carbon atom. So there is a change like this. Here there is the attachment of the nucleophile, and here the negative charge. The negative charge will be on the neighboring carbon atom. The electron pair is shifted to the neighboring carbon atom. And not electrophile, sorry, the nucleophile. And nucleophile is having negative charge. So the pi electrons will be displaced. Pi electron pair will be displaced. And it remains on the neighboring carbon atom. And the neighboring carbon atom gets, a negative charge. Okay. So the carbon atom, the neighboring carbon atom gets the negative charge. The electron pair, pi electron pair, is shifted to the neighboring carbon. The nucleophile is attached to one of the carbon atoms. Then, by the action of the nucleophile, the pi electron pair is shifted to the neighboring carbon, and so the neighboring carbon gets a negative charge. A negative charge. And it is called the negative electromagnetic effect. Negative electromagnetic effect. So when a nucleophile or a negative ion is attached to a pi bond, then it is a negative electromagnetic effect. It's a temporary change. Suppose the nucleophile is withdrawn, then the reversal takes place. The same old structure of the double bond is formed again. So this is a temporary change due to the requirement of approaching say nucleophile or electrophile. Here the nucleophile is approaching. Now you take the case of the approach of an electrophile. Say double bond here, and an electrophile is coming. E plus electrophile is coming. When the electrophile is coming to the carbon atom linked by the double bond, then what happens? The pi electron pair will be utilized. Pi electron pair will be utilized by the electrophile, and there is formation of a new structure like this. Here there is the electrophile, and from the carbon atom electron is removed, and so the neighboring carbon gets a positive charge. See, it is getting a positive charge. Okay. So it is plus effect. Okay. Plus E effect. So you remember like this. You need not bother about the minus I or plus I. Remember this. When a negative ion is attached to one carbon atom, that is a nucleophile, the neighboring carbon gets a negative charge. When a positive ion is attached, you say remember in that way, when a positive ion is attached to a carbon atom, that the neighboring carbon atom gets a positive charge. And such a change is called electron shifting. That is called electromagnetic effect or E effect. It's only a temporary change, and that's due to the requirement of the approaching reagents. Maybe a nucleophile or an electrophile. Now you come to the third one. That's called a resonance. It's called a resonance. We have already seen a resonance R. This is also known as mesomerism or a mesomeric effect. Mesomerism. Mesomeric effect. Resonance effect or a mesomeric effect. Mesomeric effect. You remember the term resonance, that is better. You know, in some cases, the properties of certain molecules cannot be explained with the help of a single structure. The properties like, say, bond length, bond length, bond energy, bond length, bond energy, etc. Such properties cannot be explained with the help of a single structure. Then such properties can be explained with the help of a number of structures. And such structures are called resonance structures or the contributing structures. Resonance structures, or they are called the contributing structures or resonance structures. Okay. And the phenomenon is called resonance. Say, for example, you take benzene. We have seen this already. Benzene. The molecular formula we know. It is a C6H6. We know the structure of benzene. Same, the benzene structure is like this. There is alternate double bond and a single bond. Alternate single bond and a double bond. And this was suggested by Kekulé. Kekulé structure. Kekulé structure of benzene. If this is the only structure for benzene, there should be carbon-carbon double bonds in benzene. If there is carbon-carbon double bonds, then benzene should be an unsaturated molecule. Remember, double bond and a triple bond, unsaturation. And it should be highly reactive. But benzene is not that much reactive. It is not that much reactive as the other carbon-carbon double bonded compounds. Say CH2 double bond CH2 ethane, highly reactive. It remember the test for unsaturation? Decolorization of red bromine water or a decolorization of alkaline potassium permanganate solution, Bayer's reagent. Bayer's test for unsaturation. So these tests are given by compounds containing carbon-carbon double bond, unsaturation. But unfortunately, benzene, it does not decolorize bromine water immediately. Change will be there under drastic conditions. Normally, when bromine water is added, there is no sudden decolorization. Or when Bayer's reagent, alkaline potassium permanganate, that is pink in color or violet in color, when it is added, it is not decolorized suddenly. It's not decolorized. That means in benzene, there is something abnormal has happened in benzene. There is no pure carbon-carbon double bond. Here, the structure is something different. Similarly, you measure the bond length. If say, if there are double bond and a single bond, carbon-carbon double bond and a carbon-carbon single bond, then the bond length in carbon-carbon bond length in benzene should be of two types. That is carbon-carbon single bond length should be there. Carbon-carbon double bond length should be there. We have studied this already. But in benzene, there is only one type of carbon-carbon bond length, 139 picometer. That is something between the carbon-carbon double bond and the carbon-carbon single bond. 154, 124, something different between these two. There is difference in the bond length. So, the bond length, you studied this already in another chapter, where electrons, say, chemical bonding, we have studied this. Okay, so here the bond length in benzene is between a single bond, carbon-carbon single bond, and a carbon double bond. So something has happened. We cannot explain these properties. Benzene is highly stable. It is that much. It is not that much reactive. It cannot decolorize bromine water or a potassium permanganate solution immediately. It is not that much reactive. Also, it is stable. All these properties cannot be explained with the help of this single Kekulé structure. So, say it was given another structure also in which the electron pairs are shifted. Say the electron pair is shifted like this. Shifting of electron pair. Say like this. Here also the electron pair is shifted. So the position of the double bond is changed. Position of the double bond is changed like this. You call this Kekulé structure number 1, and this is Kekulé structure number 2. The two structures are different. Then, if this structure, the electron pair shifts, say like this, you will get the old structure. So there is a shifting, continuous shifting, continuous dislocation of the electron pair, pi electron pairs. In this case, pi electron pairs. The pi electron pairs are continuously shifted like this. And this type of phenomenon that's called resonance. So, in some cases, the properties of molecules cannot be explained with the help of a single structure. Then the properties are explained with the help of a number of structures, and these different structures are called resonance structures. They are called resonance structures, or contributing structures, contributing structures. They are also known as canonical structures, canonical structures. So the actual structure is a hybrid of the various structures. The hybrid of the various structures. So we cannot say locate the position of the double bond and the single bond in benzene. It is something between these two. So the actual structure of benzene, it is something like this. Say it is between single bond and the double bond. Or you can show the structure by using a solid circle like this. Say the double bond that is not localized, single bond that is not localized, that is not fixed between any pair of carbon atoms. It is wandering. Say the pi electrons are wandering like this. And this phenomenon is called a resonance. And the various structures are called the resonance structures, or contributing structures, or canonical structures. And the actual structure is a hybrid. We call it as resonance hybrid. Resonance hybrid of the various structures. Resonance hybrid of the various structures. actual structure. We cannot draw the actual structure. So it can be, in the case of benzene, it can be drawn, it can be shown like this only. Okay. So hybrid of two Kekule structures. And due to this, an extra amount of energy will be released. An extra, due to resonance, an extra amount of energy will be released from the molecule. And so it becomes more stable. Do you remember? Less the energy, more the stability. Less the energy, more the stability. Due to resonance, an extra amount of energy known as resonance energy or a delocalization energy that is given out. And that much it is more stable. So the stability is increased by the release of emitting, the release of resonance energy or the delocalization energy. Now let us take another molecule. You take acetate ion, acetate, acetate ion, acetate ion. That is formed from acetic acid. You know, CH3, C double bond O, OH. This is our acetic acid, vinegar, acetic acid, or ethanoic acid. When this ionizes, CH3, C double bond O, O minus. That is our acetate ion plus H plus ion or proton, protic acid, bronzed acid. Now you consider the structure of acetate ion. You know, acetate ion is found to be very stable. That is very stable. Why is it more stable? The stability can be explained with the help of resonance. Okay. We can draw the structure this way. CH3, C double bond O, then O minus. That is one structure, one resonance structure. And in the next case, the electron pair is shifted, say like this. So you will get another, say resonance is shown by double-headed arrow like this. Double-headed arrow. So you get another structure. CH3, then C, O minus, then double bond O. That is the structure number 2. Okay. Now, if the electron pair is shifting C again, like this, you will get the old structure. So the structure is dancing between these two. See, the electron pairs are wandering between these two structures. So we cannot say what is the actual structure. That is something between these two. And that is the resonance structure. And it can be shown this way. CH3, C single bond oxygen. Here there is a single bond oxygen. And the double bond, the pi electrons. See, the pi electrons are, you can show this way also. See, the pi electrons will be wandering like this. And that is the actual structure of acetate ion, and that is more stable. That is more stable. And if it is so, what about the carbon? See, the carbon-oxygen bond. What about the carbon-oxygen bond length? Say the carbon-oxygen bond length in acetate ion will be equal. Is it not? It is equal. If structure 1 or structure 2, then the carbon-oxygen bond lengths are different. The carbon, they are giving me, the teachers are waiting here, they are giving me a signal. Okay, so let me stop now. So that is, the bond length will be equal, and that is due to the resonance like this. Okay, so the shifting of electrons like this, that's called a resonance. Various structures are called the resonance structures, or the contributing structures, or the canonical structures. The actual structure will be a hybrid of all these things. Okay. So this is also a third electron displacement. There is one more. I thought to finish it by this period. We can finish it in the next period.